all for the lecture 2 of the first half. In the first session of the today's schedule, that is introduction to metrical fixed point theory and applications, part B, particularly the applications part. I think most probably it is covered because well in time by Professor Basile Birindo. And now the next talk by the same, because as I said yesterday also, he has some obligations in Romania, and some other countries, accreditation part. So for some time he is not available in the afternoon. So the next talk is under the title Iterative Method for Fixed Points of Non-Expansive Maps. Okay. You have the contraction map and you have the ellipsis map. Now this contractive map also by Edelstein. Now this is in between non-expansive map and treatment of the non-expansive map. Normally if you talk about the norm linear space and T is a mapping from X to itself, then norm of Tx minus Ty is less than or equals to norm of X minus Y for all Xy belongs to X in case of the norm linear space, non-expansive maps. Okay. So for such maps, you cannot take the sequence of Picard's iteration and you can't move so smoothly like you are moving with the Banach fixed points. So there are some abstractions, there are some issues why the sequence can't converge, and what is the beauty in considering the non-expansive type maps, non-expansive condition also. Okay. So professor will deal with all such conditions and discuss about this. If time permit, we shall talk something else also. Thank you. Please.
All right. So roughly speaking, the first 3 lectures were devoted to contractive type mappings. Non-expansive mappings are strongly related to contractive mappings, but it is another world. It is another world, even if they are related. So I just want to make a short diagram. This will be Banach. These will be Cannon mappings. These would be Chatterjee mappings. These would be, I don't insist on them. These would be any others. And this would be almost contraction, then includes all of these and many others. And non-expansive are in this way. Of course, most of them, it could be here, maybe just a little bit there, but usually we have almost contraction which are not non-expansive. Again, non-expansive have some common parts. We'll see with quasi-non-expansive. They are included in strictly pseudo-contractive mappings, and these are included in the class of demi-contractive mappings. Anyway, this enabled me to speak to one conference with the following title: Living in the Jungle of Non-Expansive Type Mapping. And if I have time enough, I'll show a part of this jungle. There are a lot of kind of non-expansive type mappings. But essential, this class is extraordinarily important. And I would like to follow the same methodological approach. I mean, I did some, in the last years, by the way, maybe 10 years or so, I was most involved in algorithms to solve several problems for non-expansive type mappings. So this is why I want to show you how I was led to introduce a class of mappings I mentioned yesterday in the context of almost contractions. This means enriched mappings. And I would like to explain how it happened to me to see this, this class of mapping, this technique. And this is, I start by drawing your attention to this important concept in mathematics, extraordinarily important, the convex combination. All of us are familiar with the concept of convex combination, but for sure, in many chapters of mathematics, it is underestimated in the sense that we use convex combination, but we don't point out its relevance. This concept has a geometrical and linear algebra origin. It's easy. We know that the notion of convexity appears in geometry. Look, when it was first introduced in mathematics, in this almost 300 years, so in total 2,300 years before, he introduced the concept of convexity in geometry. Then the concept appeared in linear algebra as we use their linear combination. But it was a long process of evolution in essence, basically related to the development of analytical geometry, of algebraic curves, system of linear equation, and so on, differential theory of determinants and differential equations. You know, we use this concept of convex combination. Some interesting papers that I suggest is this one, a general outline of the genesis of vector space theory. It's from 1995, very interesting paper. And this nice book by Dorier, it's in French, but it means that historical analysis regarding the emergence of the some elementary concepts in linear algebra. Of course, this concept was familiar to Euler, D'Alembert, Lagrange, Cauchy, Wronski. Wronski founded this this theory for differential equations, solving linear differential equations by linear combination, not convex. And the definition we know all is very simple. We have a subset of a linear vector space V, and this set A is said to be convex if for all vectors x, y in A and for any scalar lambda in 0, 1, we have this property. The convex combination of x and y belongs to A. So this convex combination means that the sum of these two coefficients is 1. In general, we write it as ax plus by and a plus b equal 1. This is the convex combination. Fundamental concept in iterative approximation of fixed points, because 90% of the iterative methods are convex combination based. All are convex combination based. In the sense, we'll see we have such kind of convex combination of the terms appearing in a iterative method. So in general, we have this equivalent definition we can have with many scalars, but their sum will be 1. These two definitions are equivalent. So we call such an expression like this, a convex combination of the vectors x1, x2, xn. There are many fields of research in mathematics that use convex combination directly or indirectly. For example, this in fixed point theory, the relevance of convex combination was pointed out in this paper by my Professor Roos, an abstract point of view on iterative approximation of fixed points, impact on the theory of fixed point equation. I would like to tell you that we always learn from our teachers. Always learn from our teachers. My beloved Professor Roos, he, at a certain moment, he said, Vasile, you are doing this, iterative methods. I said, yes, because I am a computer scientist and he realized these are important. So once he learned from his pupils, for his students, and he did a lot of very nice insight in these iterative schemes. Because in this paper, I do recommend you, is free on this journal, Point Theory. He put an abstract point of view and he pointed out the role of convex combination, and his generalization is very nice. I have no time to show you the concept. Above the convex combination he introduced admissible perturbation. He introduced, starting from convex combination, this admissible, maybe I'll have time to, perturbation of a mapping, which is the equivalent non-linear version of this linear convex combination. Then I draw your attention in real analysis. This paper, recent paper, bounding the convex combination of arithmetic and integral means in terms of one parameter and geometric means. What is exactly what I said yesterday. We have two mathematical objects, and if we compute the average, the mean of these objects, what it results in general, it's a better object. It's a new object, and sometimes, as I'll show today, we get a very important new mathematical object. Then, in system theory, in control, this paper, which seems to be written by some Indian mathematician, new hybrid active noise control system with convex combination. Directly in the title is mentioned the Then in operations research, in mathematical programming, also researchers are using the convex combination you can see of two different search directions of conjugate method and application to image restoration. Very interesting application. Then, numerical analysis. Again, numerical analysis methods to charged. Those will have a lot of work.
You are consuming our battery.
Yes. This is why I'm saying.
Because minds are working very fast. They have to switch from mathematics to computer, computer to mathematics.
Okay. Well, all right. So next, in optimization, I mentioned this paper by my friend and collaborator Pum Kumam from, by the way, Nutapol Pakaranang was my PhD student. He spent a lot of time at my university. And they did an interesting work by combining two different techniques and by convex combination to get a better algorithm to solve minimization problems. Then in statistics, you can see again by convex combination of Gaussian processes and Bayesian analysis for deterministic computer experiments. Probability theory and stochastics, again, semi-groove generated by a convex combination of two Feller generators. The same idea, to combine in nonlinear analysis, we'll speak now. So, in nonlinear analysis, I just remind you, Professor Murthy reminded you what is a non-expansive mapping. We should work now in a linear norm space, X, with norm denoted in this way, and a map T is a Banach contraction. We know already it's a Cannon mapping. We already met it. Chatterjee mapping already met it, and is non-expansive if this inequality holds. So at the beginning, Kirk called this type of mappings which do not increase. How is the exactly the which diminished. I do not remember exactly. It's a term to refer to non-expansive mappings in the sense that they do not expand the distance between X and Y by their images. So this is the key tool of some of these mappings. For example, Cannon mappings are quasi-non-expansive mappings. Also, Chatterjee are quasi-non-expansive, and we see what does it mean. So how I discovered what I call the enrichment of non-expansive mappings by convex combination. I was, when I wrote my book, almost, more than 20 years ago, because it was the first edition in Romania published, and in Springer is the second edition. I was studying iterative methods for non-expansive mappings. And here the following concept we need. So we'll denote by T lambda the average, the convex average of the identity operator and the given operator T, which is non-expansive. We'll denote the fixed point set the same, similarly as now. And I just to tell you that I was contemplating for a long, long time these very nice results by Krasnoselsky. Krasnoselsky was an Ukrainian mathematician. Krasnoselsky means handsome guy. In Ukrainian means very handsome guy. But he was very big, he was a very tall, big guy and very handsome, really. He was a great mathematician. He did a lot of genuine results. Then Browder exploited the results by Krasnoselsky, and Ishikawa, a Japanese mathematician, he wrote a very important paper published in Proceedings of American Mathematical Society in 1976 related to non-expansive mappings. And look, what actually Krasnoselsky did in this year, 55, two remarks about the method of successive approximations. It was published in Russian, and what is interesting, this paper has been published exactly the same paper in a Romanian journal. I never I understood why. So exactly this paper was published in a Romanian journal in Russian, of course, again, but I don't know what happened. At that time, we were under Soviet influence, so maybe there was some agreement between the editors, and they published exactly the same paper in the Romanian journal. Okay.
Same type of results in SP Singh, BNAR, and Matkowski.
Yeah.
Matkowski's result is the same lemma what the SP Singh published in Journal of Australian Mathematical Society, and he published in Proceedings of American Mathematical Society. Same result, no change.
So, what is the idea? Krasnoselsky has shown that if T is non-expansive, that T lambda is also non-expansive. Very important. So, non-expansiveness is preserved by convex combination. And not only non-expansiveness, but they share the same fixed point set. So, the fixed point set of T lambda is exactly the fixed point set of T. And this enabled Krasnoselsky to construct an iterative scheme. And he noted also the following fact. This new operator, the average operator T lambda, is also asymptotically regular. This means that we have this property. The norm of the difference between T lambda the iterate n plus 1 minus T lambda iterate n tends to 0 as n tends to infinity. This means that it's asymptotically regular, but the map T is in general, a non-expansive map, is not asymptotically regular. So what is this? By using the average, the convex combination of a non-expansive map T, which is non-asymptotically regular, we get a map which is asymptotically regular. So, from the point of view of the fixed point theory, What does it mean? T lambda is richer, has larger properties than the original T. So exactly as I anticipated, by a convex combination of the identity and of the map itself, non-expansive, we get a map which has a new property, is asymptotical regularity. And this asymptotical regularity is extraordinarily important because we'll see, I don't know if I have on the next slide. No, I don't. So what is this? In general, xn plus 1 Picard iteration associated to a non-expansive map does not converge. Or even if it converges, it does not converge to a fixed point. But this new map, which means 1 minus lambda xn plus lambda t of xn, this converges to a fixed point of f. This was the main idea behind this convex combination. So we enriched by a convex combination. So this can be seen on the following simple example. Again, a simple example. Look, this map T 1 minus 6 is non-expansive, has a unique fixed point, but Picard iteration does not converge. We can see immediately. We take the initial value x0a, which is not 1/2, the fixed point, and then we get an oscillatory sequence, a1 minus a, a1 minus a, and so on. So this sequence, it's easy to see, does not converge because it is also oscillatory, but the T lambda n plus 1 minus T lambda n of x0 is exactly converges to 1/2. So is the example that a non-expansive function T and each convex combination T lambda, its average mapping is asymptotically regular. I have here an example to show the difference between these two instances. Picard iteration does not converge, and what I call Krasnoselsky iteration to Krasnoselsky. I consider Krasnoselsky was the first one to do this significantly. And we consider a very simple non-expansive mapping is the rotation of the unit disk. This means we have the unit disk, and rotation means we rotate with a certain angle. So this is the map T, rotation of the entire disk. And of course, the unit fixed point of this map is 0 because it remains fixed, and the others are not fixed points, and the Picard iteration associated to it does not converge. I illustrate it immediately, but the average map T lambda has this property, so it's asymptotically. So here it is dynamic example. So we take x0, and T of x0 will be here, Picard iteration. Then T of x1 will be x2, and it is easy to see that it will go continuously and will have no convergence to the fixed point, which is here. But if we use now an x0 this is rotation with 90 degree, to be easy to see what happened. So x0 is here, the fixed point is here, and the image of x0 is rotation with 90 degrees, an angle of 90 degrees. So this is x1 in Picard iteration, but for Krasnoselsky, what we did, we take the average. Here is lambda, I forgot to put there, is lambda 1/2. Is exactly the arithmetic mean, the average. So x1 is the average of x0 and t of x0. This means 1/2 x0 plus 1/2 t of x0. Then t of x1 is this one. We rotate it 90 degrees, it's here. Now, to compute x2, we take again this segment. The middle point is the next iteration, x2, because it's the average of x1 and t of x1, and so on. You can see that x2 already approached near the fixed point, and tx2 will be this one, x3 will be this, and we can see that the distance decreases. So the distance between the points and the fixed points decreases and will go in this way in a spiral, and this will converge to x0. This is the graphical representation of this situation. So once again, fundamental property of non-expansive mappings. Non-expansive mappings in general do not have a fixed point, but under some assumptions, and this famous fixed point theorem by Brauder, Gödde, Kirk, if the Banach space is uniformly convex, okay, we have Professor Veramani will speak about normal structure, the way in which Kirk worked on this theorem. We know it has a fixed point. Normally, we also know that in certain, under certain assumption, this set is convex, and so on. Many information. But Picard iteration cannot be used to approximate, in general, fixed points of non-expansive mapping. So this was fundamental in the class of contractive type mappings. We have seen Banach, Kahneman, all these Helmholtz contractions, we were able to approximate fixed points by Picard iteration, the simplest possible iterative point method. But for non-expansive, we should go further, we should consider more elaborate iterative schemes like this one obtained by a convex combination. So, once again, convex combination of two terms leads to convergence. So now, my methodological step. I told you when I wrote, I do wish you will write a book. Where writing a book is something disastrous for you. So work for years, lot of work. I read almost 1,800 papers. Can you believe this? Incredible. From them, I selected some 400. There were the basic literature. Then working, crazy. I'll not do this now. Hey, so working on these chapters, because I devoted in my book 2 or 3 chapters to non-expansive mappings, time mappings, all the time I had the impression something is very beautiful inside this theory. So after a while, 5 years ago, 6 years ago, I put myself this problem. Okay, if we are in the case of non-expansive mappings, this map T lambda, which is the average map, has some richer properties. What will happen if I use in a certain contraction condition, instead of T, the operator T lambda, the map T lambda, I said, what will happen? So it took me a while to put this into practice. So this what would mean? For Banach contraction, instead of T, we put T lambda. It's a new contraction condition. For Cannon, the same, we put T lambda instead of T. We put T lambda to Chatterjee, and we put T lambda in the case of non-expansive. Despite of this familiarity of mine with these conditions, I don't know why I started with this. My first paper on this kind was this. And so I was led to what is called enriched non-expansive mappings. I published this in 2019, but it took me a while until I finished clearly. So the way I introduced this class of new class of mappings was the following one. So I said, okay, I used this condition I showed you before, and this is the definition. Sorry, this is the definition. So a map T defined in a linear north space in general is said to be an enriched non-expansive mapping, or B, to show the constant, non-negative constant B enriched non-expansive mappings, if we can find a constant B such that we have this condition. This condition, in my opinion, looks very nice. If we take B0, what will happen? Is exactly non-expansive mapping. So it's quite natural condition. But look, where it comes. It comes exactly from this condition after transforming and, how to say, hiding the idea from here. So this is exactly this condition where I denoted lambda 1 over b plus 1, and we get exactly this condition. So this means we have an enriched non-expansive mapping. So as I said, it's clear that any non-expansive mapping T is zero non-expansive. So apparently enriched non-expansive mappings consist of a larger class of mappings. But we don't know if this is true. So I introduced this definition. I said, okay, what is this class? And the first point was, as I said, and I insist on that, examples. Is there any enriched mapping, non-expansive mapping, which is not non-expansive? And here is a very simple example. We take this interval on the real line, 1 over 2, 2, and consider this map. If you remember, I consider this map. They are related. Here is minus, and here is division instead of, so 1 over x for all x. This is self-mapping, and T is not non-expansive. It is easy to show. By the way, I forgot yesterday to challenge you to solve the examples I presented, one of the examples at least, but maybe we'll have a kind of session for discussion and for solving these examples. T is not non-expansive because actually T is Lipschitz map with constant L equal 4. What does it mean? This means that we do this. It's easy to see that it's and for our data, this is less than So it is actually Lipschitzian, is not non-expansive. This is not less than x minus y or equal. So it is not non-expansive, but it is enriched non-expansive. It is not difficult to show that with B 3/2 we have this condition satisfied, and it has a unique fixed point. So here is the proof I mentioned to show that it is not non-expansive. It is easier to take x1 and y 1/2, and then tx is 1, ty is 2, and norm of tx minus t1 is 1, while the norm of x minus y is 1/2, and this is not true, it's a contradiction. So we have an example of enriched non-expansive mapping which is not non-expansive. Here is the proof that it is enriched non-expansive. I don't insist on it. You can see how we proceed. We consider the definition, and in the end we found that B should be greater than 3/2, so we can work with B equal 3/2 to get this property. So the first idea is that these two classes are independent. So what is the relation? It is clear that enriched non-expansive are here and non-expansive are here, because I've shown any non-expansive is enriched non-expansive, but here we have this T which is here and is not here. So this is the point. We already enlarged the class of non-expansive mappings. It is also independent of quasi-non-expansive mappings. If you know a mapping is quasi-non-expansive if its fixed point set is non-empty and we have this condition with y a fixed point. So ty becomes y, and this is quasi-non-expansive. Quasi-non-expansive class is independent of non-expansive class of non-expansive mappings, in the sense that a non-expansive map or a non-expansive mapping which has no fixed points is generally not quasi-non-expansive, but any non-expansive map which has fixed points is quasi-non-expansive. And here is the proof. We assume T is quasi-non-expansive, and we get for the same, for x 1/2, the same contradiction. So the class of enriched non-expansive mappings, which includes all non-expansive mappings, is independent of the class of quasi-non-expansive and the class of non-expansive mappings. This class is quite large. This is a first conclusion. So all non-expansive mappings are enriched non-expansive. Some Lipschitzian mappings, as I shown, are enriched non-expansive. Some generalized pseudo-contractive mappings, it's a concept introduced in this paper by myself in 2002, and all Lipschitzian and generalized pseudo-contractive mappings are also enriched non-expansive. So, what is the main problem of fixed point theory? We have a space, a setting, we have a map, we have some properties for this map, and what are we interested to know? Sorry, if this map has a fixed point, and if it has fixed points, to approximate the fixed point. This is the problem I consider for enriched non-expansive mapping. So, to decide if the class of enriched non-expansive mappings is a class that have fixed points, and then if these fixed points exist, to construct an iterative method to approximate these fixed points. And to establish such results, I need the notion of a demi-compact operator introduced by Petrichin. Petrichin, I think he's still alive. He should be over 95, something. He's of Ukrainian origin, but his family moved in USA. He was a very good collaborator of Browder. They produced very high-level mathematics. He introduced this interesting notion of demi-compact operator to extend the notion of compactness for operators. And the notion we need it, we'll see, to get strong convergence theorems. We have a Banach space X. T is mapping. It is said to be demi-compact if for every bounded sequence xn from this domain of T, such that xn minus txn converges strongly to x, there exists a convergent subsequence of xn. This is the definition. So once again, the demi-compactness means for such an operator for which xn minus txn, if x is 0, this is related to the fixed point problem, okay, and it possesses a convergent subsequence. Here it is important to point out that some product of demi-compact operators and the product of a real or complex number by a demi-compact operator are in general not necessarily demi-compact. So this notion is very special. This was introduced by Petrichin in 1966 and was used in the approximation of fixed points of condensing set contractive mappings in 72. Here are some examples of demi-compact operators. Compact operators are of course demi-compact if we are in a Hilbert space and we have these properties, which are generally the first one called, if we are in a real Hilbert space, this is called strongly monotone operator, and these are such kind of operators are demi-compact for these values of alpha. Compact operators are mainly involved in the theory of integral operators, integral operators being the most important, perhaps, example of compact operators. When we work with Fredholm integral equations, these involves compact operators on function spaces, and the compactness property is shown by Ecke continuity. We should not insist here for our aim, it is not essential. So, other examples of such operators. Look, this is a simple example of a demi-compact operator. This is, you can see it's an example of a contractive mapping. It is not continuous, it's compact. A demi-compact, sorry, is not compact. So in the case of this space of sequences with the usual norm, then T defined in this way, I forgot to mention C is the usual orthonormal basis of L2, then this map is an isometry, is demi-compact but is not compact. So the demi-compactness is a more general property which is enough for the needs of our fixed point iterative schemes. I have here one convergence theorem for enriched non-expansive mappings. We have a Hilbert space, so we work in Hilbert space. The definition has been given in linear norm space, but as I mentioned, the Browder-Gödel-Kirk fixed point theorem is in uniformly convex Banach spaces. Here we need, for our work with iterative schemes, the structure, the setting of a Hilbert space, which you know is a particular case of Banach spaces. So we have a Hilbert space H, we have a bounded closed convex subset of H, C, and T is an enriched non-expansive mapping, which is also demi-compact in the sense of this definition. In that case, the set of fixed points of T is non-empty, is convex, and we can prove this convergence, important convergence results. For any given x0 and any number lambda, the Krasnoselski iteration scheme, which is a convex combination of xn and t of xn by lambda, converges strongly to a fixed point of t. Because t is maybe even infinite set, it's maybe an interval, even an interval. We don't know which fixed point, but in general, we know that for any x0, we'll get a fixed point. It's not denoted here. It generally depends on x0. On the starting...
Xn is weak convergence.
Sorry? No, it's strong.
Xn also strong.
No, it's strong because of this demi-compactness. It's strong. But wait. When we drop out the demi-compactness, we have only weak convergence. So this, when we have the same things, but this first result is a particular one. So at the beginning, I could prove this only for the case we have a unique fixed point, P, and then the Krasnoselski iteration 2 converges but weakly to P. So demi-compactness is essential to get strong convergence. This was the first result in Hilbert spaces in this paper. I go back because I did not put here. No. Okay, this was the paper, 2019, 5 years ago. Well, at this moment, what we can say about enriched contractions? We are here. We have enriched contractions, and for any map T, including mappings here, we know this has a fixed point, and we can approximate the fixed points by the Krasnoselski iterative scheme. But only in Hilbert space we have this property. In a Hilbert space, we establish this result. So next, I'll reach some other things, but at the moment I want to mention an extension of this result to Banach spaces from Hilbert spaces by a special treatment, and then together with my best collaborator, Madalina Păcurar, we did the same work for Banach contractions, and this is the paper published in 2020, devoted to enriched contractions, then enriched Cannon mappings, enriched Chatterjee mappings, and I spoke yesterday about enriched almost contractions, which is the general, including all these classes of enriched mappings. What else? In convex metric spaces, the convexity, we know it's a structure of convexity. I use the convexity in the sense of Takahashi, and we produce this class of enriched contractions, contractive mappings in convex metric spaces, and we are led to this very important paper. I mentioned at the opening ceremony about saturated classes of mappings and unsaturated classes of mappings. So, we did also enriched Chirich-Reich-Rus contractions. Then some collaborators of mine, Abbas and Anjum did his PhD only on enriched mappings. I would come back to this concept of saturated and unsaturated. Okay, we worked a lot, you have seen. We did a technique of enriching for Banach, for non-expansive first, then for Banach, for Cannon, for Chatterjee, for Chirich-Reich. And all the time, if you look into these papers, you'll see that we always shown that Banach contractions are here and enriched Banach are here. So we enlarged. But I produced a paper where the original class was strictly pseudo-contractive mappings. And I published it. And after a while, I realized that the enriched strictly pseudo-contractive actually is exactly this. Is not enlarging. Okay. At this point, I realized not any class of mappings can be enriched by this method. I mean, by doing this process, considering the T lambda instead of T, in a contraction condition, we do not always obtain some new results. And this pointed us to this concept of unsaturated and saturated classes of mappings. As I mentioned, I was inspired by the concept in chemistry. I was good in chemistry. In my first year of high school, I was very good. In Romania, at that time, we have high school 4 years. After first year, the best students were selected to follow an elite class. So a special class of mathematics was called. So I was selected for both class of mathematics and chemistry, but I've chosen mathematics. And in this class of mathematics, I had a teacher, a lady, we did not love each other. So it was something. So I did not study chemistry, just to survive. But the punishment for me was, in the end, I married a chemist. And you'll not believe, I don't know, maybe you have this in India too. We have some meetings after 10 years of graduating high school. Do you have? 10, 20 years to celebrate, 20 years of the graduation and so on. And this is a very nice meeting of classmates and the teachers.